All right, in this lesson we're going to learn about how pH and basically how acidity works. To start this off, we have to actually take a look at just water by itself. Now, this is kind of a strange idea, but technically, whenever you have a pure, very pure sample of water, meaning we're not talking about bottled water where they say the purest spring water. We're talking about if you were able to chemically generate water that's not got any sort of dissolved ions, vitamins, minerals, nothing in it. The purest water actually is a very weak electrolyte, meaning it's going to self-ionize. So what that looks like is that you have a water molecule is going to bump into another water molecule, and they're actually going to exchange a proton. One will accept it, one will, again, give up that proton, that hydrogen ion. It doesn't really matter which one does which, but just know that this does happen on a very minor scale. Now, what happens again is that now you have H3O plus and OH minus. Well, what do you know about those? Both those substances, H3O plus, hydronium, hydroxide, those effectively represent the amount of acid or kind of the base that's around. And if you notice, they're actually going to be the same amount. These two amounts are very small, but again, quite present. They're there technically. So this again is an example of what we call self-ionization of water. Actually, this is the self-ionization of water. Not really any other substances that do this. So what do we do with this? What do we learn from this? Well, know that if pretty much with any aqueous solution, right? Again, thinking outside of just pure water, but any solution of any kind that has stuff dissolved in it, there will always be some amount of hydronium and hydroxide present. So in pure water, though, if you're looking at the purest of pure water, the concentration of each are 1 times 10 to the minus 7th and 1 times 10 to the minus 7th. Now, that's for each of these ions. Go ahead and commit that to memory because that's going to be a nice sort of baseline to use. We'll talk about why that's significant later on. Now, you also have this new thing, this ionization constant of water. This is going to be something that we just simply abbreviate to just Kw, right? K is some sort of a constant, W for in water, and that's going to be equal to the concentration of H3O plus times the concentration of OH minus. So this is happening for any solution, any one single solution. These two values multiplied by each other will equal to some Kw. Now, for pure water, right, since we know the value of H3O plus and OH minus are just these two right here, we're going to stick those in these spots. If you do that math, that would look like basically a quick little calculation to give you 1 times 10 to the minus 14th. So ultimately, one thing you need to remember is the formula that this thing right here, right, is equal to anytime you want to solve for Kw, you can stick those two in. But also, Kw is a constant, so anytime you're given one, you can get the other. And go ahead and commit this guy to memory as well. Now, let's go and see how this looks in terms of acidic versus basic. In pure water, as we saw earlier, the concentration of H3O plus and the concentration of OH minus are the same. We saw that both of those have a value of 1 times 10 to the minus 7th. In this way, the water is described as neutral. This pure water is described as a neutral solution. However, when the two concentrations of these ions are not equal, then you either have an acidic solution where the H3O plus is greater than the OH minus, which kind of makes sense, right? A hydronium associated with acids, hydroxide associated with bases. So if you have a greater concentration of hydronium compared to hydroxide, it's considered an acidic solution. On the other hand, if it's basic, that means the H3O plus concentration is less than OH minus. Ultimately, regardless of the relationship greater than, less than, if you take those two concentrations and multiply them by each other, they should always equal that Kw, which again, as a reminder, something you should first of all memorize, but also it's always going to be 1 times 10 to the negative 14th power. Let's put this into action. So let's say we're given a solution that contains 5 times 10 to the minus 9th molar hydroxide ions. 1. Calculate the H3O plus concentration. All right, well, let's go and see what we got. I know that Kw, which is always equal to 1 times 10 to the minus 14th with no units, that's equal to the hydronium ion, which I don't know, so let's go and write that in as a variable, times 5 times 10 to the minus 9th molar. Notice how I left off the bracket, right? I used regular parentheses for this for the concentration value, but again, to represent the concentration itself of hydronium, I just went ahead and left the brackets in. To solve for that, I go ahead and rearrange. The ion concentration, or the hydronium ion concentration anyway, is going to end up being 2 times 10 to the minus 6th molar. Now, is the solution acidic, basic, or neutral? Well, let's go and see what happens if you compare these three. H3O plus concentration for the solution, 2 times 10 to the minus 6th. I got to see is it greater than or less than 5 times 10 to the minus, okay, let's try that again. Hydroxide OH minus, which one's bigger? Well, let's take a look at the numbers one more time. One thing to keep in mind here is that we're talking about this. That's probably your best bet, right? The numbers in front are nice and all, but having this value of 10 times something tells us generally a better scale. So if you see here, 10 to the negative 6, 10 to the negative 9, which one's a larger value? Well, obviously, negative 9 seems like it's bigger than just 6. 9 and 6 are different. But of course, the negative sign basically kind of flips them. So the larger value actually ends up being the 10 to the negative 6th, larger than the 10 to the minus 9th. So back to this original inequality I'm trying to figure out, right? H3O plus, that's a greater concentration than OH minus. So this solution is considered acidic. So that's basically how these problems work. This next one right here, using a solution where NaOH has a concentration of 3.9 times 10 to the minus second power. Calculate OH minus concentration, calculate H plus concentration, and then determine if the solution is acidic, basic, or neutral. We'll start with the first part. So sodium hydroxide, this one has a concentration there, right? Well, that's not exactly the same thing as hydroxide concentration, but it's, pretty easy. Remember that sodium hydroxide, that's a substance that separates into its two component ions. One dissolved in water because it's a strong electrolyte. So we know at least from just kind of knowing this, that they split up into two ions. Now, how exactly does it help us out? Remember, it's a 1-to-1 ratio, so it's a 1 here in front as a coefficient. It's a 1 here as a coefficient in front of the OH minus. So if I have the concentration of this guy, I can also get the concentration of hydroxide. That's going to look like 3.9 times 10 to the minus second molar. Do a little bit quick mole ratio for every 1 mole of sodium hydroxide. That says sodium hydroxide. There will also be 1 mole of hydroxide ion that generated. So that means the concentration of the hydroxide ion is 3.9 times 10 to the negative second power molar. How about solving for AH plus? Well, let's try this out, right? We're forgiven if we have this value here. By the way, this is one of the answers, so let me go ahead and box that guy. Let's go ahead and set it up to where I can solve for use KW to solve for the concentration of H3O plus, setting it up to where I have 3.9 times 10 to the negative second molar. All right. KW, and go ahead and replace that with 1 times 10 to the minus 14th. Solve for H3O plus, you end up getting a value of 2.6 times 10 to the minus 13th molar. All right. Let me also do note, since we're talking about significant figures, the original number, that is only 2 significant figures. This doesn't play into it at all. And so that means you have 2 significant figures here. You have 2 significant figures there, so it all works out the way it's set up. Finally, let's compare the two amounts, H3O plus versus OH minus concentration. Again, looking at the factor, the exponent here with 10 to the negative second, 10 to the negative 13th, 10 to the negative second. That's a much larger value than 10 to the negative 13th. So which one's greater in concentration? OH minus is greater in concentration versus H3O plus. Therefore, this is a basic solution. Here's some more practice problems. Go ahead and give those a shot. Make sure you can apply these on your own. But let's go ahead and talk about how pH figures into all this. So pH is effectively the power of hydrogen. It actually comes from a French phrase. I'm not going to try to pronounce that. Just kidding. I am. Pouvoir de hydrogen. Let's go with that. That's the negative of the logarithm of the hydronium ion concentration in solution. Okay, so let's kind of break that one down. First of all, on the next page, let's go and see what that formula looks like so it's not so messy. pH is equal to negative log of hydronium ion concentration. So this pH is just going to be some value. That's equal to the negative log, right? It's a function of this concentration of H3O plus. That'll give you pH. Now, just for the sake of, again, comparison, a lot of times you'll see it written as the negative log of H plus, right? But of course, they more or less mean the same thing. H plus is just a shortcut way of writing H3O plus. In pure water, the concentration of H plus is 1.0 times 10 to the minus 7th. What's the pH of pure water? Let's try that out. pH is equal to the negative log of 1 times 10 to the negative 7th power. Plug that in your calculator. pH, that's equal to, I don't know, 7? What? Well, yeah, that's pure water, right? Pure water is supposed to have a neutral pH, and it's going to have a pH of 7 because the concentration of H plus ion, which is the same as the concentration of H3O plus ion, is 1 times 10 to the minus 7th. Hence, 7. A solution contains a hydroxide concentration of 3.34, yada, yada, yada. What is the pH of the solution? Is the solution acidic or basic? Well, I don't have a actual, hydroxide or hydronium ion concentration, but I do have hydroxide, right? So if I have a hydroxide, I can conceivably figure out the hydronium concentration. Remember using this guy, all right? So I'm just going to write this formula out just to remind you where I'm getting it from. You should be able to plug things in appropriately, and eventually you'll find that the H3O plus concentration is 2.99 times 10 to the minus 12th molar. And so, we got to figure out the pH. pH is equal to 11.5, right? Oh, let's make sure I know how to get that done. That's going to be the negative log of 2.99 times 10 to the minus 12th molar. Solve for pH, that's going to equal to 11.5. And that's your answer here. All right, so the question is then, is the solution acidic or basic? Well, we have one of two ways of doing this. One, you can look at the H3O plus versus the OH minus concentration and see which one's bigger, right? You can see 10 to the minus 12, 10 to the minus third. Yeah, you can make that call. Or you can use this nice convenient little number right here, 11.5. That's above 7. 7's a neutral mark, so that's going to end up being a basic solution. Now, one thing I did not go over, I figured some of this at least looks familiar to you, but let me just cover this. Remember that this scale goes all the way from 0, pH scale goes from 0 all the way up to positive 14, where 7 is smack dab in the middle. That means it's neutral. And since that solution we just looked at has a pH of about 11.5 in this range, it's well above 7, so this solution ends up being basic. If it ends up being below 7, it ends up being acidic. All right. So here's some practice problems. Give those a shot. See if you can get the same thing that's listed down here at the bottom. Be careful about how concentrations are calculated. So if pH is the negative log of hydronium ion, what about pOH? pOH is very much a thing. So in this case, pOH is equal to pH is equal to negative log of the hydroxide concentration. So functionally, mathematically, it's the same thing. It's now using hydroxide ion instead of hydronium. And also, one more thing that's kind of nice to know is that for any one single solution, pH plus pOH is always equal to 14. This is nice to know. It's nice to memorize. So let's try this out. Determine the pH and the pOH of a solution where NaOH is equal to this. All right, so there's a couple of strategies here, but let's go through one or two of them. First of all, I'm going to do the work up here. If my sodium hydroxide concentration is equal to 1.77 times 10 to the minus 4th molar, I'm going to do a little shortcut. And just know that your hydroxide concentration, that's going to equal to 1.77 times 10 to the minus 4th molar. Now, let's go ahead and walk through this. First of all, they were asking for pOH. Well, pOH, how do I do that? Well, pOH is the negative log of hydroxide, which is equal to 3.75. That's equal to pOH. Then, if my pH and my pOH is going to be, or the sum of the two is equal to 14, then that means pH is equal to is going to equal to 10.25. All right, solving for pH. And that's basically it. The alternative, though, is that if I were given OH minus concentration, I could conceivably then also do the concentration of H3O plus, and that's also an option. Now, that will give you a value of 5.65 times 10 to the negative 11th molar. But, that's not what the question's asking me for. However, I do know that if I take this concentration and apply the negative log to it, I can get that guy. So really, it's just kind of another way of doing this work, but it's totally up to you. The original way, probably a little bit more efficient, a little bit less time consuming, so maybe you try that. So that's that answer, and that's that answer. All right. Let's finish this out just real quick, going backwards. If I were given a pH, how could I maybe figure out the H3O concentration? Well, basically, you're doing the inverse. If you were to recalculate this and kind of rearrange how this worked, the concentration of H3O plus basically is 10 raised to the negative pH. So let's see how this works. If a solution of HCl has a pH of 3.08, what's the concentration of HCl? All right, let's try this out. Well, first of all, if I'm given a pH of that, one thing I can solve for is the H3O plus concentration. That's equal to 10 raised to the negative 3.08. What calculation does that give you? That gives you 8.32 times 10 to the negative 4th molar. Now notice how this is actually H3O plus concentration. The question is asking me for a solution of HCl. Well, again, I know that HCl is a strong acid because HCl, when it dissolves in water, it will generate hydronium ion and chloride ion. So that means I know that if I have this value present, I can do a little bit of stoichiometry to get that kind of working backwards there. So the work I'm going to do here is 8.32 times 10 to the negative 4th molar for every 1 mole. actually write this in H3O plus. For every 1 mole of H3O plus, I know it takes 1 mole of HCl from the original sample. And do some math here. Hopefully you'll find that the answer is pretty easy to calculate. 8.32 times 10 to the minus 4th molar HCl. And that, my friends, is your answer. And to wrap this up, a couple of notes. We're only going to use strong acids and strong bases in this class. Anything beyond that, it's a little bit more complicated with weak acids and weak bases. Also, we're going to stick with monoprotic strong acids. So our polyprotic ones, for example, H2SO4, that one's actually a little bit more complicated because it has 1 strong proton. So the other one, therefore, is weak. And that's, again, a lot messier, so we're not going to deal with that. Finally, this would be a nice little chart to help you keep things organized. This is basically a little cycle that helps you know that if you're given one of these, you can figure out the rest, right? For example, what does it take to go between pH and pOH? Well, knowing that pH plus pOH, that's equal to the value of 14. How do you go from pH to H3O plus? What's the relationship there, right? You either have the negative log of H3O plus, right? That's equal to pH. Or alternatively, if you need to, you can also know that the concentration of H3O plus is equal to the 10 raised to the negative pH, right? What we just did a minute ago. Going between H3O plus and OH minus, you know this involves Kw. And then going back and forth between these two, we know that involves either the pOH equaling the negative log of the concentration of OH minus, or that the concentration of OH minus is equal to 10 raised to the negative pOH. And that just keeps things organized, so you'll know when to use what during what kind of problem you're given. Finally, there's a little bit of mixed practice here. This covers everything we've just done, and that'll do it.